morning. It's Friday, July 25th. I'm out here at the National Scientific Ballooning Facility in Palestine, Texas. We are awaiting a balloon launch. The weather is a little sketchy and our flight's been postponed a couple of times already, so we're really hoping to get it up in the air today. Behind me is the gondola that will accept our cosmic ray experiment. Our experiment will actually go right in here inside an American Tourister suitcase. It all packs up pretty nicely. What we're trying to do is replicate the discovery of cosmic rays. Cosmic rays are a little bit of a misnomer. Cosmic rays are charged particles with extraterrestrial origins. By extraterrestrial, I don't mean aliens, but I just mean from the sun, from other stars, particularly from supernova. The way cosmic rays were discovered, like some great discoveries in science, was by accident. It was widely known that there were radioactive minerals that could be found on the Earth, and in fact purified. This is the pioneering work of the Curies. So it was presumed that the source of radiation was in fact from the Earth. And what Victor Hess did, he had an instrument, which I'll talk about in a moment, to measure radiation coming up from the ground. A lot of activity behind it. So the idea was pretty simple. Get in a balloon, ascend, and he did some very high altitude and dangerous ascents without breathing apparatus, 20,000 feet. The amount of radiation that he was able to detect should get less and less and less as he went up and up and up. In fact, the opposite turned out to be true. The radiation got more and more and more as he went up and up and up. Is the Earth the source of all radiation? Well, Hess's experiment showed pretty clearly not. And for that he won the Nobel Prize some years later. Hess's instrument was pretty simple. He used what's called an electroscope, basically a way of measuring electric charge. Electroscope has two very thin leaves. You could make one out of cellophane tape. And if those leaves are charged, they will repel each other because they have the same charge. But it was known for a long time that over time, if the electroscope is left undisturbed, the leaves will gradually come back together, indicating they've lost charge. Where did the charge go? Radiation, ionizing air molecules, and those ionized or charged air molecules then draw the charge off the leaves. So the rate of charge loss would indicate how much radiation is actually present. I had a colleague try to reproduce this experiment on a balloon with a really beautiful antique electroscope, and could not do it. It's a very, very difficult instrument to use. You're trying to actually measure through a very tiny eyepiece minute changes in the deflection of these leaves on a bouncing balloon. Very problematic. Our detector is rather more modern. We've got pieces of plastic, rectangles of plastic, and that plastic is doped with a fluorescent molecule. If you were to hold it out in the bright sunlight, it would turn purple. But our plastic, if a charged particle goes through it, it gives off a very faint light, and that light can be detected by a photomultiplier tube. Basically a piece of electronics that's sensitive to even one photon, and then can bump that up into a robust electric signal, which goes into a board, and the board goes beep when it gets a hit. Well, these things are kind of noisy. When you operate them right at the threshold. By noise, I don't mean you can hear it, but noise, I mean in the sense of creating spurious data on their own. Sort of like when you turn up your stereo all the way to 10 or even higher to 11, you hear hiss. And the hiss isn't, it's not signal, it's just noise. And there, in that sense, it is noise as well in terms of hearing. So the way we get around that with these instruments is we use two of them, one above the other. And that way, if one goes off and the other one goes off within about a 10 nanosecond window, we are reasonably assured that in fact we saw a signal. Now this is a bit of a black box, and we did some validation work in the last week over at the assembly room, including what happens to count rate if your detectors are like this versus like this. Well, if most radiation is coming from above, the count rate should be much higher than when they're like this. And in fact, that's true. We see that in our detectors. Another thing that I was able to do last week is go for an airplane ride. And we climbed up to about 10,000 feet. What do you suppose happened? Count rate went up. So putting our cosmic ray experiment onto this gondola right here behind me, which is hanging from the drop-off truck, and we're hoping to have a flight today. Our flight's been postponed a number of times because of weather, and it's still pretty sketchy.